Unlock the power of Android app development with this comprehensive tutorial on sensors, camera, Google Maps, and location services using Kotlin and Jetpack Compose. Learn how to leverage Android's Sensor Manager for motion, position, and environmental sensors. Create a compass app with accelerometer and magnetometer data, and capture photos using the Camera app or CameraX. Master location, services with the fused location provider, and display dynamic Google Maps with markers in the Find Me app. Packed with practical Kotlin code examples, Jetpack Compose UI techniques, and step-by-step guidance, this tutorial is ideal for refreshing your programming knowledge or exploring productivity tools for mobile development. Exploring Sensors, Camera, and Location in Android Development by the Programming Professor. Let's start by reviewing the high-level structure of what we'll cover. First, we'll introduce the Android sensor ecosystem and how it's used in mobile apps. Then, we'll build a compass app powered by motion sensors. After that, we'll move on to the Camera and Photo Express apps, where users can take photos, adjust brightness, and save them. Finally, we'll develop the Find Me app, which uses location services and Google Maps to show the user's real-time position on a map. Android devices are equipped with several sensor categories. Motion sensors like the accelerometer and gyroscope track movement and rotation across X, Y, and Z axes. Position sensors measure orientation and magnetic fields, helping determine direction. Environmental sensors monitor physical surroundings like temperature and light. If you're using the Android emulator, virtual sensors can simulate these values so you can test your app without real hardware. To work with sensors programmatically, Android provides a complete framework under the Android.Hardware package. This framework enables you to list available sensors, check their capabilities, and capture real-time data. The Sensor Manager class provides access to system sensors, while the Sensor class describes individual sensor properties like type and manufacturer. You interact with these through methods like getDefaultSensor and getSensorList. Each sensor provides key information through metadata fields. For example, you can retrieve a sensor's name, type, and vendor. There's also a min-delay value, which determines how frequently the sensor sends data. A min-delay of 0 means the sensor only sends data when changes occur. Otherwise, the sensor streams data continuously, making it useful for apps that monitor changes in real time. It's important to note that sensor availability varies between devices. Most phones include an accelerometer, but more specialized sensors, like barometers or humidity detectors, might not be present. To handle this variability, declare sensor requirements in your manifest using Uses feature. This ensures only compatible devices can install your app through the Play Store, helping avoid crashes and confusion. Once your app knows which sensors are available, it can begin listening to data. This is done by implementing Sensor Event Listener. This interface has two callback functions. One handles accuracy changes, and the other receives new sensor readings. Each sensor event includes values, a timestamp, and a reference to the sensor that generated the data. This information is essential for real-time sensor-based apps. To demonstrate this in action, we'll explore a proximity sensor demo. This example app uses a custom Android sensor class that abstracts away low-level sensor handling. It integrates with a view model that starts and stops sensor updates and exposes the latest reading as a state variable. You can find this sample in the GitHub repository linked in the course materials. The view model listens for proximity sensor changes and updates a proximity state variable accordingly. This value can then be used to drive UI components, such as displaying proximity readings to the user. The view model uses factory-based initialization, so it can cleanly receive dependencies like the proximity sensor. It also ensures the sensor is stopped when the app is paused, conserving system resources. The Sensor app Composable provides a UI for this feature. It displays the current proximity value on screen and uses lifecycle resume effect to manage when sensors start and stop. When the app resumes, the sensor begins listening. When the app pauses, the sensor listener is removed. This design ensures efficient battery use and proper state management during lifecycle transitions. The accelerometer is one of the most common motion sensors. It measures acceleration from gravity and movement along X, Y, and Z axes. You can use it to detect tilt, motion, and even steps. The output is measured in meters per second squared. Because of Earth's gravity, the accelerometer always returns a value unless the device is in free fall. Another essential motion sensor is the gyroscope. It detects rotation speed around each axis, typically in radians per second. If the device is stationary, the gyroscope outputs zeros. When you rotate the device, values update to reflect the rotation direction and velocity. The Android emulator allows you to simulate these changes in the extended controls menu. Our next app, the Compass app, demonstrates how to combine accelerometer and magnetometer readings. The magnetometer detects Earth's magnetic field. Paired with the accelerometer, it helps determine the device's absolute orientation. These sensors work together to point to magnetic north regardless of how the phone is tilted or rotated. It's important to distinguish between true north and magnetic north. True north refers to the geographic North Pole, where all longitude lines converge. Magnetic north, however, is based on the Earth's magnetic field and currently lies in northern Canada. The difference between these two poles can vary by hundreds of kilometers and changes over time. To start building the Compass app, use the starter project available on GitHub. This project includes the basic structure for Android Studio, with organized packages for UI, sensors, and logic. You'll begin by adding your own sensor classes and implementing the app's Compass logic using existing skeleton files. The manifest file declares required features with uses feature. This ensures the app only appears on compatible devices. When you run the starter app, the compass rows should appear centered but stationary. You'll add the logic to make it rotate based on sensor data. Next, create two new classes, one for the accelerometer and one for the magnetometer. These classes extend from a shared base class called Android Sensor. Each class specifies the sensor type and checks for feature availability on the device. You'll use these classes throughout the app to get live data. To wire everything together, initialize both sensor classes in the Compass application class. Then inject them into the Compass view model. This architecture separates logic from UI and makes your code more maintainable and testable. To make our Compass app responsive to the user's physical orientation, we need to calculate which direction the phone is facing and rotate the compass rows accordingly. This is handled in the Compass view model using a method called compute rotation. The function receives real-time data from both the accelerometer and magnetometer, two motion and position sensors that help determine tilt and direction. We pass those values into Android's sensorManager.getRotationMatrix method. This method computes a 3x3 matrix that transforms coordinates from the phone's internal reference frame to the world's geographic coordinate system, where the x-axis points east, the y-axis points to magnetic north, and the z-axis points upward toward the sky. Once we have this matrix, we call getOrientation to extract three key angles: azimuth, pitch, and roll. The azimuth is the one we're interested in. It tells us the angle of rotation around the z-axis. In compass terms, this represents the direction the top of the device is pointing relative to magnetic north. We convert this azimuth from radians to degrees and then negate it, because rotating the image clockwise requires a negative angle in Compose. The result is a smooth, real-time update to the compass UI that reflects the phone's heading in the real world. To enable this rotation logic, we need to ensure that sensor values are being collected and stored efficiently in the compass view model. This is done through mutable state and live listeners. Inside the view model, we declare a mutable float state called rotation, which stores the angle used to rotate the compass rose. We also create two mutable lists, Excel values and magnetic values, to hold the most recent sensor readings from the accelerometer and magnetometer. When the view model's start listening function is called, it registers listeners for both sensors. Each time new data comes in, it updates the corresponding list and calls compute rotation to recalculate the azimuth angle. This ensures that every small change in orientation is reflected in the UI without delay. The stop listening function unregisters these listeners, which helps reduce battery usage when the app is paused or not in focus. By managing this data flow inside the view model and using Compose's reactive state management, we create a highly responsive and resource-efficient compass. This pattern of sensor input, state tracking, and reactive UI updates is a powerful model you can reuse across many Android apps involving real-world input. To visually reflect device orientation changes in the Compass app, we need to rotate the compass rose image according to sensor data. This rotation is driven by the rotation value exposed by the compass view model. Inside the Compass app composable, we pass this rotation to the image composable using the modifier.rotate function. This modifier takes the rotation in degrees, with positive values rotating the image clockwise and negative values rotating it counterclockwise. To ensure the app reacts to lifecycle changes, we also use lifecycle resume effect to start and stop sensor listening based on the activity's state. When main activity resumes, the app begins receiving updates from the accelerometer and magnetometer. When the activity pauses, it stops listening to conserve battery. If you're testing the app on an emulator, you'll need to simulate device orientation. In the emulator's extended controls, set XROT to -90 so the device lies flat, like a phone held horizontally. Then rotate the Z-axis to simulate compass movement. On a real device, just physically rotate the phone and observe the compass rose aligning with the Earth's magnetic field. This setup gives users an intuitive and responsive compass experience based on actual sensor readings. Let's now shift focus to the camera. Today's Android devices typically include at least two cameras, a front-facing camera and a rear-facing one. The front-facing camera is commonly used for selfies, video calls, or facial recognition, while the rear camera offers higher resolution and advanced features for photography and video recording. Android supports two primary approaches for accessing camera functionality in apps. The first is using the built-in Camera app, which you can launch from your app to capture images without directly interacting with the camera hardware. The second is CameraX, a Jetpack library that gives developers fine-grained control over the camera stream, including real-time previews, analysis, and image capture. For the purposes of this walkthrough, we'll use the simpler built-in Camera app, which allows for rapid prototyping and reduces the need for extensive camera permissions and configuration. To enable basic camera usage in your app, you must declare a camera requirement in your app's manifest file. This is done using the Uses feature, tag, specifically targeting android.hardware.camera.any. This tag ensures that your app is only installable on devices that actually have a camera. If your app relies heavily on camera functionality, This is critical to prevent runtime failures on unsupported devices. Importantly, if your app uses the built-in camera app solely through activity result contracts, such as launching the camera for a preview image, no additional permissions are required. This eliminates the need to request runtime camera access, which can often lead to unnecessary user friction or hesitation during onboarding. To capture a preview photo without managing storage or files, use Jetpack Compose's Remember Launcher for Activity result in combination with the TakePicturePreview contract. This creates a launcher object that you can call from a button or gesture. When triggered, it launches the default camera app. After the user takes a photo and confirms it, the camera app returns a small bitmap thumbnail. This is ideal for apps that need a quick visual result, like a profile picture selector or a content previewer, without needing to handle file storage, file paths, or permissions. The simplicity of this contract makes it an excellent starting point for beginners working with camera integration. In addition to capturing new photos, you may want to let users select existing ones. Android supports this with the Media Picker, a built-in UI that allows users to browse and select photos or videos from shared storage. This interface is automatically sorted by creation date and can be filtered to show only images. When the user selects a photo, the picker returns a content URI, a secure reference to the chosen file. You can display this photo in your Compose UI using Coil's Async Image Composable, which handles image loading, caching, and rendering with minimal configuration. This method is preferred over manual bitmap decoding and scaling, as it handles lifecycle awareness and performance optimizations out of the box. In this slide, we take a closer look at how to implement image selection using Android's built-in Media Picker. The Photo Picker Demo Composable allows users to select an existing photo from their device's shared storage, such as pictures taken previously or downloaded from messaging apps. Inside the composable, we define a mutable state variable, photo URI, to hold the result of the image selection. We use Remember Launcher for Activity result along with the Pick Visual Media contract to create a launcher that opens the Media Picker. This contract is flexible. It can be configured to allow images only, videos only, or both. In our example, we use the Pick Visual Media request to restrict selection to images only. When the user taps the Select Photo button, the picker is launched and presents a system UI for browsing their media library. Once the user chooses an image, the picker returns a URI, which is stored in Photo URI. That URI is then passed into Coil's Async Image Composable, which loads and displays the image. This approach is efficient and elegant, and it eliminates the need to manually decode bitmaps or manage permissions. It provides a modern and secure way to integrate photo selection into your Compose-based Android apps. The Photo Express app takes all of these ideas and brings them together into one cohesive experience. It allows users to capture a photo, preview it, adjust its brightness, and then save the final result to shared storage. This provides a realistic example of how to combine camera input with image editing and media storage. You'll learn how to build UI components that respond to state changes, handle user interaction in real time, and interact safely with the Android file system. To get started, download the Photo Express Starter project from GitHub. This project includes a well-organized architecture, separating concerns into UI, data, and logic layers. In the data layer, you'll find an image repository class that handles bitmap manipulation and file creation. In the UI layer, you'll work with composables like Photo Express App, Photo Screen, and the App Bar. Your job will be to wire up these components with the view model, implement the photo taking flow, and connect the brightness slider to image rendering and saving logic. The user interface, is structured to be intuitive and minimal. At the top of the screen, the top app bar contains two action buttons, one for launching the camera and one for saving the edited photo. Below that, the screen displays the captured image using async image, which reflects the current brightness level using a lighting color filter. At the bottom, a slider allows the user to control brightness from dark to light. The layout uses standard Compose techniques like scaffold, column, and padding modifiers to ensure a consistent experience across devices. When users interact with the slider, the photo is updated immediately to reflect the new brightness level, providing a smooth, responsive editing experience. Before the user can take a full-sized photo using the Camera app, the Photo Express application must first prepare a place to save it. This means creating a unique, writable file in external storage before the photo is taken. This file acts as a container where the Camera app will write the photo. Using Get External Files dir with the Pictures directory ensures that each image is stored in a location the app can access later, while remaining private to the app until explicitly shared. To securely share this file with the Camera app, Android apps use a file provider. This component generates a temporary, secure URI that other apps can use without exposing the internal file path. This is important because Android does not allow direct file sharing across apps. FileProvider.getURI4File generates a content URI from the image file, which is then passed to the Camera app when launching the Take Picture contract. This setup allows the image to be written by the Camera app without violating Android's security model. For the file provider to work, the app must declare it in the Android manifest.xml file. A provider element is used, and it must match the authority string used in your code. This authority is typically formed by combining the app's package name with .fileProvider. The attributes exported equals false and grant URI permissions equals true ensure that only trusted apps using the URI have access, and only while the system grants it. Alongside the manifest, you also need to define which files can be shared via the file provider. This is done with a file paths.xml resource in the res/xml directory. This file includes a paths element that maps directories to symbolic names used internally by the file provider. For instance, the external path element allows access to files in the app's external storage. This config makes sure your app can convert the image file into a usable URI. With this system in place, the view model defines a method called TakePhoto to orchestrate the process. It calls createPhotoFile to generate the image file, updates the app's internal state with the photo URI, and returns the URI so that the UI can launch the camera with the proper target. A companion method, photoTaken, is called once the Camera app finishes, and it marks the photo as visible again in the UI. To launch the camera, the app uses the Remember Launcher for Activity Result function with the Take Picture contract. This sets up a one-time launcher that takes a URI and opens the Camera app. The URI passed to it is the one returned from TakePhoto. When the user captures a photo, the result is a Boolean flag indicating success or failure. If successful, photoTaken is called to finalize the operation. The app allows the user to change the brightness of the captured photo using a slider. This is achieved through the Lighting Color Filter class. This class applies lighting effects to each pixel in the image by multiplying and adding color values. The slider controls the strength of these operations, simulating lightening or darkening without altering the original image file. In the Image Repository class, the method createColorFilter translates the slider value into color changes. If the brightness is above a midpoint of 100, it increases the RGB values, making the photo brighter. If it's below 100, it scales the values down, making the image darker. This gives the user a seamless range from dark to bright using intuitive controls. To apply these changes, the view model includes a method called change brightness. This method receives the slider value, computes the appropriate filter using the repository, and updates the UI state accordingly. It also marks the photo as unsaved, which enables the Save button and signals to the user that changes haven't yet been stored. The UI component photo screen connects this logic to the user interface. It displays the image using Coil's async image, passing in the current color filter from the view model. The slider's onValueChange callback is wired directly to change brightness. This allows the image to update in real time as the user moves the slider left or right. Once the user finishes editing the photo, they can save the new version. Although the Save Altered Photo method isn't initially wired into the app, it demonstrates the correct approach. This method applies the selected brightness filter to the original bitmap, draws the result on a canvas, and saves the image as a new file. This workflow preserves the user's visual edits. To make the saved image visible outside the app, it must be written to shared storage. Android provides the MediaStore API for this purpose. MediaStore manages metadata like image names and paths and makes photos discoverable by other apps. This is how apps like Google Photos or Instagram can access your saved images. In the Save Altered Photo method, the app uses content values to define properties like file name and MIME type. It inserts this data into the MediaStore using a content resolver, which returns a URI where the image will be saved. The app opens an output stream at that URI and compresses the filtered bitmap into it as a JPEG. The view model wraps this logic in a Save Photo method. This method is marked suspend because it runs on a background thread. Once the repository finishes writing the photo, the view model updates the UI state to reflect that the photo has been saved. This disables the Save button, giving visual feedback that the operation was successful. In the composable UI, the Save button's on-click handler is connected to Save Photo using a coroutine scope. This lets the app perform the file saving operation without blocking the main thread. It ensures that the UI remains responsive, even during longer file operations on slower devices. After saving, open Google Photos or your device's gallery to confirm the result. You should see the photo appear as a new thumbnail. The image also shows up in Android Studio's Device Explorer under /SD card/pictures. Because it's stored in MediaStore, the image stays on the device even if you uninstall the app. Many modern Android apps rely on knowing where the user is. To accomplish this, Android provides access to a variety of sensors and data sources for location tracking. While most devices include a GPS sensor, they often use a combination of technologies to determine the device's position. For example, when GPS signals are weak, such as indoors, Android can fall back on Wi-Fi networks or nearby cell towers. This hybrid approach helps improve accuracy and power efficiency. Android developers typically use the Fused Location Provider for this task. This is an API from Google Play Services that combines GPS, Wi-Fi, Bluetooth, and cellular data into a single location source. It handles the heavy lifting of determining the best signal to use at any given time. Developers simply request a location with a desired level of accuracy and frequency, and the Fused provider delivers the best available result. For example, a rideshare app may request high-accuracy updates every second, while a weather app may only need to know the user's city once per hour. Before your app can access the device's location, you must declare the proper permissions. Android provides two distinct levels, coarse and fine. Coarse location uses low-power sources like Wi-Fi and cellular data to approximate the user's location, typically accurate to a few hundred meters. Find Location, on the other hand, uses GPS to provide precise coordinates, often within a few meters. Both permissions are classified as dangerous, which means they must be explicitly granted by the user through a runtime prompt. In your manifest file, you need to include both permission tags, one for Access Find Location and one for Access Course Location. This allows the app to request the appropriate permission dynamically at runtime, depending on its current needs. If the user grants only course permission, the app should adjust its behavior accordingly and provide fallback logic to handle less accurate data. At runtime, you can check whether permission has been granted using context compat.check self-permission. If permission has not been granted, you can launch a permission request using Remember Launcher for Activity Result in Jetpack Compose. This launches a system dialog asking the user to allow or deny the location request. The result is returned as a Boolean flag, indicating whether access was granted. This process ensures user control and aligns with Android's security model. Once permissions are handled, it's time to retrieve the device's actual location. You do this using the Fused Location Provider client, which is initialized using locationservices.getFusedLocationProvider client. This client exposes two common methods. The first is last location, which returns the most recently known position. This is usually fast and power efficient, but it may be outdated if no app has requested a location recently. The second is get current location, which actively requests a new reading, offering better accuracy but at the cost of more power and time. Before building location features, you need to include the required dependencies in your app module's build.gradle.kts or build.gradle file. The first is Play Services Location, which provides access to location APIs. The second is Kotlin X Coroutines Play Services, which allows you to use location requests with Kotlin coroutines for asynchronous programming. This setup ensures your app can retrieve locations efficiently without blocking the main UI thread. Testing location-based apps can be challenging without a physical device, but Android Studio's emulator provides excellent tools for this. You can use the Extended Controls window to simulate device location. You can manually drop a pin on a map to set the emulator's coordinates or upload a GPX or KML file that simulates a route. These features are helpful when testing features like navigation, geofencing, or live tracking. The Find Me app demonstrates these concepts in practice. It uses the Fused Location Provider to retrieve the user's current coordinates and displays them on a map. The map is rendered using the Maps SDK for Android, which is part of Google Play Services. This SDK provides a fully interactive map, complete with markers, zooming, and pan gestures. To use the Maps SDK, your app must include a valid API key. This key links map usage to your Google Cloud account and helps track requests for billing and analytics. Although Google does not charge for light testing or development use, your key should still be kept secure. If leaked, someone else could abuse it and cause billing charges. You can also configure restrictions in the Google Cloud Console to prevent unauthorized use. To get an API key, sign into the Google Cloud Console, create a project, enable the Maps SDK for Android, and create a key. The key should be copied into your app's Android manifest.xml inside a metadata tag. During development, it's okay to remove usage restrictions, but in production, you should limit the key to your app's package name and signing certificate. The Find Me Starter project includes two main Kotlin files. The first, main.activity.kt, initializes the UI and renders both the permission check and map screen. The second file, findmeapp.kt, contains the composables that handle map display and interaction. When you open the starter project, remember to replace the placeholder API key with your own. To add a Google Map to your app using Jetpack Compose, you'll use the Google Map composable provided by the Maps Compose library. This composable allows for a rich set of configurations, such as camera position state, which manages where the camera is pointing and its zoom level. You'll also provide a content description for accessibility, and optionally use properties to control the map style and zoom bounds. The on-map-click parameter is useful if you want to respond to taps on the map, such as for adding markers or retrieving coordinates. You initialize the camera position using camera position from lat lng zoom and store it using remember camera position state so that the camera persists during recompositions. Before using this API, ensure that the dependency for Maps Compose 6.1.1 is added to your Gradle build file so your project can access the necessary components. Next, let's integrate this Google Map into your actual application layout. In the Find Me app.kt composable, initialize the default camera position centered on Singapore using its latitude and longitude. You create this using camera position from lat lng zoom with a moderate zoom level to show the city. Then, you set up a fused location provider client instance using location services.get fused location provider client context. This client will later allow you to fetch the device's actual location. The camera position is stored using remember camera position state, which helps preserve map state across recompositions. Finally, you render the map using Google Map and supply the camera state to center it appropriately. While testing, you may suppress missing permission warnings with @suppresslint with a missing permission input, but this should be removed or properly handled in production code. In this code update, you flesh out the Find Me app composable to wire together all necessary components for showing the Google Map. The default camera pose is defined at the top using coordinates for Singapore. Within the composable, you initialize the context and create the location client using Google Play Services Location Provider. Then you set up the camera position state using Remember Camera Position State, providing the default position so the map starts centered. Inside the Google Map block, you provide this camera state and leave room for overlays or markers later. A launched effect block is also present, indicating that location logic will run once when the composable is first composed. This setup forms the foundation for dynamically updating the map once real location data is retrieved. The Google Maps SDK also includes a built-in feature called the My Location layer. When enabled, this adds a default UI element to the map, usually a button in the top right corner, that allows users to center the map on their current location. When tapped, the map displays the user's position with a blue dot. This feature is convenient for basic map navigation, but comes with limitations. Specifically, while it visualizes the user's location, it does not provide the app with programmatic access to the underlying coordinates. As a result, if your app needs to store, analyze, or react to the user's current location, this layer is not sufficient. That's why in the Find Me app, we rely instead on the Fused Location Provider client, which provides full control over location retrieval and handling. To programmatically move the camera to the user's current location, you animate the camera using the camera position state.animate function. This method takes a camera update object, which can be created with camera update factory.new lat lng zoom. To implement this, you retrieve the device's current location via the fused location provider, convert it into a lat lng object, and pass it to the camera update. Then, call animate on the camera position state with a specified zoom level and optional duration in milliseconds. This provides a smooth visual transition to the new location. You'll typically wrap this logic in a launched effect, so it runs once the app has permission and the location is available. This approach ensures the user always sees their position centered in the map when the app starts. Once you have animated the map to the user's location, it's often helpful to visually indicate the current position using a map marker. In Jetpack Compose, this is done with the marker composable, which you place inside the Google Map block. The marker is controlled via marker state, which keeps track of the marker's position. You create this state using Remember Marker State, so it persists across recompositions. You can optionally add a title to the marker, such as "Here you are," which appears in a small info window when tapped. This marker complements the animated camera update by giving users a clear, static point indicating their exact position. It also serves as a visual anchor that persists as they interact with the map. The full code for this integration is completed by updating the findme-app.kt file to include both the camera animation and marker logic. The composable defines the camera position state, a mutable variable current lat_lng, and a marker state. Inside the Google Map block, it conditionally renders the marker only if current lat_lng is not null. This prevents any rendering issues if the location has not yet been retrieved. Then, within a launched effect, the fused location provider fetches the current coordinates. These values are converted to a lat_lng object, stored in current lat_lng, and assigned to marker state.position. The camera is then animated to zoom into the new location with a smooth transition. This results in a fully functional and responsive map experience that automatically centers on the user's position and drops a helpful location marker. In this module, we brought together several of the core Android features, sensors, camera, image manipulation, and location services into a cohesive and interactive set of mobile apps. We began by exploring the Android sensor framework and built a compass app using accelerometer and magnetometer data to detect orientation and magnetic north. Then we created the Photo Express app, which demonstrated how to launch the camera app, retrieve a photo, apply brightness filters using lighting color filter, and save altered images to shared storage using Media Store. Finally, we developed the Find Me app, which integrated the Google Maps SDK and the fused location provider to track and display the user's current position. Through the use of Camera Update Factory, Camera Position State.animate, and Marker, we gave users a dynamic, interactive way to visualize their location in real time. These examples showcase practical ways to combine hardware access, system services, and UI composition using modern Android APIs with Jetpack Compose. By the end of this journey, you now have the foundation to build powerful, sensor-aware, location-based mobile apps that are reactive, user-friendly, and ready for real-world deployment. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.